Okay, welcome to part 2 of escape velocity. This is where we're working towards deriving the equation to actually calculate the escape velocity for Earth and for other planets, any other planet. So the first thing we're going to do is now consider our own thought experiment after having considered and analysed Newton's thought experiment. Now let's consider this particular situation. We have a projectile and it's launched away from a very massive object, the Earth, and it's launched in a vertical direction. So what is happening to the projectile, for example, in this case a basketball, when it's thrown upwards? Have a think about it, pause it, and then come back to the video. So if we think about everything that we've learnt so far, we know that what goes up must come down, and we're dealing with things like height, and we're also dealing with gravity, and we're also mixing into all of that energy. So let's consider energy a bit further. What is happening to the energy, or how is energy converted in that scenario? Again, pause it, have a think about it, and then keep watching for my discussion. So we can really consider two things here, kinetic energy and gravitational potential energy. And we know that they can be linked and one can be transformed to the other, but the total amount of energy is always conserved. So at the top, or at a greater height or greater distance from Earth, the object has a higher gravitational potential energy and lower kinetic energy, and vice versa. Now, let's consider if we had a velocity large enough to actually never come back down or escape this pull of Earth's gravity. Don't forget that the force of gravity is inversely proportional to the distance away, and also this distance increases, the force decreases at an inverse rate. So the further away you get, the less and less and less the force of gravity will become. So it's actually hardest or more difficult to escape that pull of gravity the closer you are to the Earth's surface. So that's the hardest part, is just getting that first bit, and then it will actually become easier and easier. And the problem is, we'll come back to it, but part of the problem is, if you imagine now we're talking about launching a rocket, the mass of the fuel is greatest at the point at the Earth's surface. So we're battling with greater forces, and then we have more force due to just the mass of the fuel. Okay, so what are the factors that we need to consider? The mass of the Earth, the radius of the Earth, or the distance between the two objects, and gravity itself. And that brings us to the final part, which is deriving the relationship. So we can see from the first line here that the total amount of energy is conserved, or will come back to a null value, and that the kinetic energy and the potential energy are the two components of that energy total that is just being converted. Then we can see, or we can use the equation of circular motion as one part of the force that is keeping the object in orbital motion. That's supposed to be a circle. And we also know that that's also the same as the force that's providing that circular motion is the same as force due to gravity. And that's the other equation here. And when we put them in, as in the circular motion equation is linked to the kinetic energy, and the potential energy is linked to the force of gravity equation, then we can, and they're both equal to 0, or they're conserved, so one will equal the other, then we can basically get to the third line, where are you, mouse, and add this negative to the left-hand side to get this equation equaling this equation. What have we removed? We've also removed mass 1 from both sides, which is the mass of the projectile, or whatever it is actually trying to leave or in orbit. And so we come up with square this side, or square root, take the square root of this side and rearrange the equation, and we're left with this. The escape velocity equals the square root of 2 times the gravitational constant times the mass of the Earth, or whatever planet you're talking about, divided by the radius, or the radius of its orbital path, or the distance between the two. So it has nothing to do with the mass of the projectile, or the mass of the rocket, or the mass of the satellite. It has only got to do with the mass of the Earth, which is why it is constant for anything trying to leave the gravitational field of that planet. And each planet will have its own escape velocity, and anything that reaches that escape velocity is free.